Thank you very much, Brian. And good morning, everyone. And okay, sounds good. It's like, you know, the air traffic controller, right? Anyway, it's my pleasure to present you today a little and very short overview of our beamline and its main strengths, its in-situ capabilities. Well, 17BM, it's a rapid acquisition powder diffraction line, and it's a very new program to the IPS ring. It's actually the program been started in 2013, and it's been started by Greg Holder, and it's been transferred from 1BM to 17BM, where we're located now. This right pretty much we've done a couple of months ago. We installed a new monochromator on it in station A. It's a new Bragg-Lowe mono, which allow us to go easily change the energy between 27 and 55 keV, and these high energies will provide us, first of all, will allow us to do samples with higher absorbance and thicker samples, and of course wider range of the sample environments. But the overview of the beam experimental station is right here. You can see the beam comes here. Here's your detector, and that's where your sample is located. Little bit about new mono. Again, new mono being installed. It works really great. It's a really great improvement from what we had before. Before we had mono which works around 17 keV, and we have a quite large optical system. We have collimating mirrors and double crystal mono, and then focusing mirror. You can imagine a lot of motions, a long time to warm up the entire optical systems. Now our beam actually, since we start running it, it's been extremely stable, and which is extremely important for the in-situ measurements. So you want your intensity to be constant all the time. And pretty much now we don't use our mirrors at all. All the focusing is done by the mono itself. And you can see it can be easily done. This is an image of the beam in station B, unfocused, and this is focused beam. Focusing works really, really nicely. And again, we increase our resolution of the data. Okay, but how do we collect the data? Again, as you saw, we have an area detector. So what we pretty much do, we just shoot the X-ray beam to our sample and collect the powder pattern, 2D powder pattern via area detector. Our beam, X-ray beam size, we usually focus it to about 500 microns, and after that we actually can cut it down to a size with a set of the pinholes, and our set of pinholes can be between 50 and 500 microns, depending on your needs. Again, the distance between your sample and detector can be easily modified, again, depending on your needs, what's the Q area you're interested in, how big is your unit cell, or how small is your unit cell, and we can move detector between 200 millimeter and 1.3 meter. We're using pertonometer detector with amorphous silica and graphite window, and therefore our data collection times are extremely short, and that's where the rapid acquisition comes into play. So our average data collection times for the materials is between 0.1 and 60 seconds. So you can imagine we can collect a lot of powder data at very short time. When you receive the image on on our detector, we receive 2D powder data. After that, what we do, we calibrate the image, and by introducing the calibration parameters such as actual detector, sample to detector distance, tilt of the detector, and so on. After that, we integrating the data and receiving actual 1D powder data. But again, we are rapid acquisition powder diffraction lines, so we collecting a lot of those powder diffraction data, and therefore we not just very rarely analyzing just single powder diffraction data, so we usually collect a lot of them and stack them up and producing so-called top view plot or counter view plot, where we can easily see any structural changes in the material and what's going on during your particular experiment. Thanks to Brian and Bob, now this calibration and integration is done automatically within the Jesus2 environment, and therefore pretty much what user gets, it's the user places a sample, set up the parameter of experiment, and at the end he sees the top view plot automatically, so he can directly see what happens with the structure of his material during the course of the experiment. Okay, well, this is the data collection, so I will pretty much redirect you to the same picture, but what is our main strength? Again, since we're collecting data very rapidly, we can explore how your material changes during some particular conditions. And therefore, we have a lot of sample environments to explore that. One of the common sample environment what we have is a float cell, where you usually place the material inside the capillary and place this cell in a beam. It have the gas in and gas out ports, and therefore you can put your material in any particular gas atmosphere of your interest. It can be easily combined with a furnace, and therefore you can study your material within temperatures between 25 and 1000 degrees Celsius. Well, if you're interested in low temperatures, well, the furnace can be easily removed from this float cell, and you can place on our beamline a cryostream, and therefore you have an opportunity to study your material at low temperatures between 100 or 500 Kelvin. Going next, if you're interested not at atmospheric pressure of gas, but on a higher pressure, we have a syringe pumps. Syringe pump can be easily again connected to the same float cell, and therefore you will be able to study your material. At least at our beamline, we done studies up to 600 bar of gas pressure. Again, how I told you, the float cell have entrance and exit ports. So the exit port of the float cell can be connected to the mass spec or residual gas analyzer, and you can study the composition of the gases, what coming out of the cell, which is extremely useful in the in-situ catalysis studies. Well, but we operating not just with a float cell. We perform experiments at our beamline by study different electrochemical systems with as an MPEX cell. If you're interested in a high pressure measurements, in terms of diamond and with cell high pressures, we have that. Our diamond and with cell can go up to 10 GPa. And again, since we can collect data rapidly, you don't want to collect so much data from just one sample, you can imagine you can do high throughput measurements and collect lots of data, but from different samples. So we do have access to the sample changer and collect multiple samples very rapidly. And just recently, we acquired a Raman spectrometer, which will be introduced in our program probably in the next cycle or so, and where you will be able to do the powder diffraction, and vibrational spectroscopy measurements at the same time. So you can see our beamline is lucky enough to have lots of different sample environments, and therefore you can pretty much remodel or accommodate our line to the system of your particular needs and explore the structure of the material at your particular applicable conditions. And I'll just gonna give you a few examples how we do it and what data we can actually extract. One of the common materials which we study at our beamline, it's metal organic frameworks, and you can imagine they have a very large unit cells, very porous structure, and therefore they have numerous gas storage and gas separation applications. And for these materials, the float cell actually works ideally. For example, we can study the metal organic frameworks under different pressure of gases. And how I told you, we can take our float cell, block one end of it, put the pressure gauge there, other end connect to the syringe pump with a gas of interest, and syringe pump would change the pressure inside the cell. You could observe it on a gauge, and during the entire time while you do it, you shoot X-rays on your material and collect diffraction data from it. What is really great, this can be easily combined with a cryostream system. Therefore, you will be able to measure the how the structure of a material changes both from temperature and pressure at the same time. And okay, so we can set up the system, and the users immediately would see that, and they would see from the top view plots how the materials is actually reacts to different gases under pressure. How we can show in this example is with the helium, the MOF didn't had any effect on the structure of its on its structure, while in terms of when we use the methane and argon, we can clearly see the powder pattern peaks moving with the pressure and they're returning back while we release the pressure, and therefore we can see the effects of the gas pressure on the MOF itself. But again, we are crystallography technique, and therefore we not just can explore how the powder pattern peaks moves, we can actually explore in terms of the structure, and therefore we also can determine where the gas molecules located inside the MOFs and identify particularly places and gas absorption sites inside those MOF while you push the gas at the high pressure inside them. But again, we actually not just can determine location, but since we collecting this powder data all the time up on all the pressures, we can easily see how the gas molecules actually goes inside the pressure inside the MOF pores at any particular pressure. So it gives us detailed insight view what's actually going on with the gas molecules inside the metal organic framework. Now we can use this data, right, and actually try even to push a frontier of science, and that's what we did with collaboration with Cambridge Structural Data Center, as they had ideas that there was no actually any structure measured with the neon atoms within organic or metal organic environment. And well, we used the same system, and we placed neon in our syringe pump, and we actually been able first time determine the structure which contain neon atoms within within the MOF. And we also determined that there is actually at low temperature and high pressure, there is interaction between neon atoms and transition metals. And this is actually the Fourier difference map of the which shows the position of the neon atoms, and this is the structure of the MOF, and the red represents the position of the neon atoms inside. But what is very important here is that such measurement have been we've been able to do it only by powder diffraction and by applying both low temperature and the high pressure. Okay, now what I'm gonna do, I will take the same system, but I slightly redesign it. And we're gonna fit it to study completely different set of material. So we'll take the same float cell, we will install the switching valve, which will switch between methane and air, or some oxidizer gas and some reducer gas. The gas will go in, goes through a sample, goes out, and we will put our mass spec or a residual gas analyzer to determine what is actually coming out of it. We will fit it with a furnace, which allow us to heat the our sample, and voila, you got excellent setup to study any heterogeneous catalysis system, because by shooting X-rays on your sample, you will be immediately, you will be able clearly see what the structural changes gonna happen with your material upon either reduction or oxidation cycle. And at the same time, you will be able to easily track the products of the reaction which being catalyzed with a mass spec. And such study have been done also quite recently at our beamline, where they studied this lanthanum, strontium, iron oxide for the oxygen storage properties, and they been able very clearly see from powder diffraction of that how the material structure changes upon oxidation or by the reduction. But at the same time, they combine data with residual gas analyzer, and they've been able to determine, so they run several samples, and they've been able to determine at which doping of strontium into this oxide will give them the best results. Okay, and I think this concludes my short overview of the 17BM program, and unfortunately I cannot speak about the all sample environments, but I just want to tell you, huge thank you for everyone who brings support to our research program. And first of all, I want to tell thank you to Winchen Hu, who is the second beamline scientist at the station, and without whom this work couldn't be done. Thank you very much.
Okay, we do have time for a few questions or comments. Hello?
What's the size of the focus beam when you open up? I know you can cut it.
Yeah, it's actually about 500 by 500 micron. Yeah, with all the, like, you know, trash and stuff, but after that we cut it down with the slits. And
So what's normal?
hmm?
What normally is the size?
Oh, before, it was.
Right now.
Right now we are operating at 300 micron. We did the experiment recently with Antonio dos Santos from SNS. He was using the diamond anvil cell, and we cut it down to 100 micron.
How long does it take you to collect data with 100 micron beam?
Actually, not that long, about 30 to 60 seconds. And currently we're using 27 keV. That's at which energy we are.
Okay. Oh.
Yeah?
Yeah?
How straightforward is it to change the, I mean, you're able to go between 27 and 50 on a KV. Yeah. Would you be able to switch energies, would you be able to use your time, or is it supposed to?
let's say that right now we actually explore the limits of our mono, and I guess we still studying this mono, and the more you do it, the faster it becomes. But actually, it's the motors on the mono is actually very, very stable, and yeah, first I think the first switch in energy took us maybe eventually like entire day to do it, but the second one is so much faster because we know what to expect, and the third one even faster than that. So I think eventually, like every user will be able to choose their own wavelengths if they needed to. Thank you very much.